techniques, machine learning for engineering applications. So I would like to express my sincere gratitude to the management, principal, head, Department of Mechanical Engineering for their continuous encouragement and support in organizing such academic initiatives. This FDP has been organized with the objective of enhancing the knowledge and the research capabilities of faculty members and the researchers in the emerging areas of optimization techniques and machine learning for engineering applications. So we are delighted to welcome our distinguished speaker for today's technical session, Dr. M. Udaya Kumar, Professor, Joint Director, Amirda Viswa Vidyapeetham, Amirdapuri Campus. So welcome you, sir. Uh, we warmly welcome our faculty members and the participants who have joined in this FDP program from various institutions. So it's time for a welcome note for the speaker. So we are truly honored to have with us Dr. M. Udaya Kumar, Professor and Joint Director, Amirda Viswa Vidyapeetham, Department of Mechanical Engineering, Amirdapuri Campus. He is a distinguished academician and eminent researcher who has made remarkable contributions to the field of mechanical engineering. So Dr. Udaya Kumar has published more than 250 peer-reviewed research papers in reputed national and international journals and conferences. His research interests mainly focus on manufacturing technology, advanced materials, and precision machining. So, which are vital areas in modern mechanical engineering research and industrial development. In addition to his research contribution, he actively serves the academic community in various capacities. He is an editorial board member of several reputed journals, including Journal of Advanced Composite Structure and the Journal of Cleaner Engineering and Technology. He is also a National Executive Committee member of the Indian Society for Technical Education, New Delhi, and a section executive committee member of SA India Southern Section. Dr. Udaya Kumar has successfully handled several research projects funded by prominent agencies such as DST, DRDO, UGC, DAE, the Ministry of Environment, Forest and Climate Change, and Poland Science Academy. He has delivered numerous research talks and invited lectures in various institutions, particularly focusing on research proposal preparation and technical paper writing, which have greatly benefited young researchers and faculty members. His outstanding contributions have been recognized with several prestigious honors. Notably, he has been listed among the world's top 2% scientists by Stanford University, so, received by Best Faculty Advisor award from SA India Southern Section, and has also been recognized as a top Indian Society by Career 360. So he is also active member of several professional bodies, including Society of Automotive Engineers, Indian Society for Technical Education, Institution of Engineers, and the Indian Society for Non-Destructive Testing. So we are indeed privileged to have such a highly accomplished researcher and academic leader among us today. His insights and experience will certainly inspire all the participants and enrich our knowledge in the field of emerging research and innovations. We are honored to have with him us today to deliver a session on the topic of machine learning, prediction of surface roughness in sustainable machining. Now I invite Dr. M. Udaya Kumar to deliver a technical session. Sir, the session is yours.
Yeah, thank you, sir. Thanks for your introduction. Shall I share my screen?
Yes, sir. Please, sir.
Are you able to see the screen?
Yes, sir. It is visible to everyone, sir.
Yeah.
Yes, sir.
So, good morning, all of you. So, today's topic is on machine learning prediction of surface roughness in sustainable machining. This is a supposed to a comprehensive presentation about a part of my student PhD thesis, and also how you have to collect information. Will go for some modeling and all. It is typically a case study. Mainly, I understand that the people from various institutions and the composition is mixing of several departments, and very particularly, this particular work is on sustainable machining, which is relevant to mechanical engineering. But the concept which I am going to present, you can understand how to go for this kind of machine learning in your domain approach. It may be, it need not be for mechanical engineering component alone. It can be applicable to all the department, right? Just understand the concept of how it should, how you have to propagate your work according to the to achieve these approaches. Why machine learning? Machine learning models are essentially because they automate tasks, improve accuracy and efficiency, and provide valuable insights from data, especially when dealing with large volume or complex pattern. This is the underlying point here. Large volume of data or complex pattern. So they can learn from data without being explicitly programmed, adapting to new situations and improving performance over time. This makes them particularly useful for predictive modeling, fraud detection, personalized recommendations, etc., etc. If something went wrong, so definitely the prediction will be the, it will not be work, right? It should be a very challenge to the people, those who are involved in this predictions and all. So we have to take a number of data that should be a reliable one. That is very important. As far as this case study is concerned, this is about the machining. Just understand the concept of what are all the parameters associated in the machining, right? You keep in mind, this is not only for this is not only for mechanical engineering. I am talking about the work which I did, right, according to the requirement. Thus, you have to understand the concept how we have to go for this kind of approaches. This first one is CISI 11. Hot or tool steel is a vital material. This is the material for manufacturing of machining tools and dies because of its greater hardness, toughness, and wear resistance. That is the material component. That is the material. Then milling is the process. Milling is operation. The machined surface is created by advancing the workpiece towards a rotating cutting tool. It plays a crucial role in production of dies, mold. The major challenge in hard milling process are short tool life and poor surface integrity. This is very important. So tool life and surface integrity. Nowadays, so optimum utilization of all resources is very important. Right? Underutilization and overutilization both are dangerous. So we have to take in account about how to arrive this optimum utilization or effective utilization. Milling center. A milling cutter is a rotary cutting tool used in milling machines to remove material from your workpiece by means of multiple cutting edges. So that continuous removal of materials takes place. It is not a metal adding process, just additive manufacturing. It is a metal removal process. So the new layer of surface will be exposed, right, after cutting the material from the workpiece. So milling input parameters. What are the input parameters I took for my study? It is about the cutting speed, feed rate, and depth of cut. Cutting speed, the cutting speed refers to the rate at which cutter moves through the workpiece. The feed rate refers to the distance of the cutter travel in a single cycle. Depth of cut, as usual, how much I am going to remove the stack, right, from the workpiece. It may be 0.1 mm or 0.5 mm, so something like that. It depends on this one. So here you can see the milling performance parameters. So cutting temperature, surface roughness, and chip. So these are all output responses. Earlier case, the three parameters what we have discussed, that is the input parameter where it is under our control. So according to the requirement, we can go for we can choose which level you want to do for the input parameter. Output response, it is beyond our control. So cutting temperature, surface roughness, and the chip. Cutting temperature arises from tool workpiece friction and material deformation, impacting workpiece integrity, tool life, and cost. Surface roughness. Surface roughness is the measure of the microscopic irregularities on a machined surface, influencing its texture, quality, and performance. So here, what you heard, there may be ups and down on the surface. So waviness, people used to say. The matting component, if it is a matting component, we have to be very clear about the surface finish. Then only the assembly will work. Unless otherwise specified, we can take the general tolerance, right? But it depends on the case to case where it is going to apply. Chip, yeah, chip is the material removed during the machining due to the machine, and it is controlled is crucial for smooth, high quality machined surface, right? So since it is a brittle material, we cannot go for the long chips, right? So it should be a short, and we have to take in account about how the chips are removed from the workpiece material, and as far as this chip nature is determined the surface quality or surface texture, etc., etc. So lubrication in milling process, right? So there are dry milling without any lubricant. You are going to do the machining operation. So ambient air acts as a coolant. Under the high speed and feed conditions, it leads to higher temperature because it is a friction. Tool and workpiece, when it comes to contact, it is friction generated. When friction continuously happens, the temperature keep on increases, right? So by at one point of time, the temperature will play a critical role, right, in metallurgical point of view, right? There may be chance for subsurface crack or otherwise maybe the phase changes. So those things and all happen. So in order to overcome this one, we can go for the lubrication, right? The higher temperature, the degrade of surface quality, and the accelerate tool wear. Tool wear also decrease. In flood cooling system are integrated with the machine tool to provide a continuous coolant flow during repetitive machining cycle. Drawbacks of flood cooling, so it is mineral-based oil are widely used in flood cooling for metal cutting. But the low biodegradability causes environmental pollution. It is another issue. Prolonged exposure also poses high risk, health risk, including skin disorders, etc., etc. There is a hazardous atmosphere. It will make a hazardous atmosphere for the workers. This is about the MQL system. Here, lubrication in milling operation, minimum quantity lubrication that we have to ensure, that we have to use. For this purpose, MQL, it is abbreviated as minimum quantity lubrication is abbreviated as MQL system. This is overcoming flood cooling. Unnecessarily excess coolant is used in this case without having any calculations, right? So that is should be avoided here. MQL method delivers a precise mixture of compressed air and cutting fluid in minimal quantity, which is then directed in the machining zone, exactly in the machining zone, right, through a nozzle. So the cutting zone is cooled by passing this one, so the temperature is remain constant throughout the machining process. So it serves as a sustainable machining technique, offering ecological, economic, and operational benefits. So now you can see this is a typical sketch representing about the MQL system, how it can be used for this. So there should be a cutting fluid. So it is a recommended one. Say for example, it may be some oil, that mineral oil we are using, right? So that compressed air, it comes into mixing chamber where the quantity, pre-measured quantity of oil is mixed with this one, and it should be passed through the nozzle at the cutting zone. Now, this is about the vegetable oil in the MQL system. Vegetable-based oil are greatly attractive replacement for mineral-based cutting oil since they are renewable, eco-friendly nature, and easily decomposable. Vegetable oils such as soya bean, etc., sunflower, sesame oils, and all natural fatty acid in this oil in the form of strong adhesive film on metal surfaces, reducing friction and wear. So we cannot eliminate friction and wear, right, at any point of time, right? Without friction, we cannot walk, right? If the surface there is no friction, we cannot walk. So minimum friction should be there. That depends upon the type of flooring where we are going to. In case of mud surface, the friction should be more. If it is mosaic, if it is tiles, right? So different coefficient of friction will be there, right? But friction is essential in our day-to-day life. Without friction, we cannot stop the vehicle. So we can minimize as far as possible. So vegetable cutting oil along with MQL technique offer excellent environment friendly and green sustainable machining. Sesame oil, it's a natural vegetable oil delivered from sesame seeds, widely recognized for diverse applications. Rich in antioxidant and fatty acid, it offers excellent lubrication and biodegradability, etc. It has health benefits such as reducing inflammation, swelling, and promoting the healing of inflamed skin. Now, the thing is, we are going to use nano-based cutting fluid and graphene nanoplatelets. It is for the cooling purpose, right? That we are using in the milling process. So, why I am giving this much information in this case study means you have to understand what is what. Merely we cannot do this optimization tool, right, without having real-time data. The real-time data is very important in getting the reliable results. So if it is the case, you have to double check about the experimental results. Experimental results, if you want to perform, you have to take the proper survey. That means you have to design, experimental design. It is very important. So now we are using this one. Then again, the question is, I don't know how many research scholars are attending this one. The novelty. Novelty is very important in your research, right? What is the new thing you are going to find? What is the deliverable? The deliverable where it is going to be used. Who will be the benefiter? In those days, it was not much attracted by the researcher. Now it is a big question by the similar interest group people. Maybe like that, right? So merely academic research will not work it out. That means you are getting funding and you are submitting the report and publishing paper. One person is getting PhD. It is not what you call perimeter at present. You have to work for commercialization. You have to go for tie-up with the industry. So which industry should get benefited? What is the benefit to the public society? That means weavers can be benefited, or farmers can be benefited, or the people in hospitals, right? So they are benefited. These are all the target group. So by using my research, these people will be get benefited. So that is very important in presentation scenario. The nanofluid is the combination of base fluid and nanoparticle. The cutting fluid property is enhanced by adding the nanoparticle in terms of convective heat transfer coefficients, viscosity, thermal conductivity, and thermal diffusivity. Nanoparticles enhance oil retention in the cutting zone, reducing surface roughness, tool wear, and cutting temperature. Right? The cost expensive of nanofluid is offset by minimal use through the MQL system. There are several nanoparticles are there, MOS2, GNPS, and HBN, AL2O3, etc., etc. So graphene nanoplatelets, which is two-dimensional layered structure, exhibit exceptional wear resistance and friction-reducing properties, making it is a highly effective lubricant. This graphene high chemical stability, shear capability, and impermeability enhance lubricant performance. Its ultra-thin structure and superior mechanical strength make it is an ideal disperse. The incorporation of graphene into lubricant enhances their anti-friction and wear-resistant properties, establishing it as a promising nano-lubricant. In that way, our approach went. Right, so there is a MQL system with the nano particle, right? That is a new thing, novelty. That is for the machining application. That is a conventional machining. We are not going for any advanced machining process. That process is very conventional machining, but we are using a new technology, right, for enhanced to get the enhanced property. Now you have the different methodology, Takuchi method, ANOVA, and machine learning models. You're all aware about these things, right? The Taguchi method is the robust design approach focused on improving product and process quality by minimizing variability. The Taguchi three-stage design process includes system design, maybe conceptualization, parameter design, optimization for robustness, and tolerance design. It is a balancing cost and quality. ANOVA is a parametric statistical method used for comparing multiple data sets to determine significant differences. It evaluates cutting parameters, impact on response variable to identify key machining factors. Then machine learning model are complex algorithms that use data to identify underlying pattern and relationship. They learn from past data to make predictions or decisions without explicit programming. Now the proposed work, how we have propagated the work. A significant gap exists in research addressing the performance of milling operations on AASAH11 steel using GNPS enriched sesame oil within MQL system, graphene nanoparticle. This is graphene nanoparticle system enriched in sesame oil within MQL system. Limited studies explore the potential benefit of sesame oil in advanced machining applications. There is limited research on the incorporation of cutting temperature analysis in MQL and NMQL environment. So how we have arrived at this one? This is based on the thorough literature survey. Now, research scholar, you please note it. So when you start your research, right, your first thing is identifying the coursework examination and all, right? Parallelly, you have to start your review, right? That means literature collection. So thorough literature is very important, and you have to submit a review paper before starting your experiment. So why I'm saying this one is the review paper will give more confidence, right, on your research work. So this is from the review, I identified this is the gap, this is the objective. Based on the objective, I have coined, based on this objective, I'm going for the experimental study, something like that, right? So it will give more confidence. And also when you go for a presentation, you can keep in touch with the similar interest group, and the network will give a lot of information how to proceed your work and all. Research on predicting cutting temperature and surface roughness in MQL machining environments using advanced ML model such as RFR and KNN remains largely unexplored. Additionally, limited studies have investigated the implementation of grid search cross-validation for hyperparameter turning to optimize model performance along with the use of more than 3 metric scores for comprehensive evaluation of ML models. Now it is the objective. So to conduct end milling experiments on AASAH11 hot die steel and evaluate the performance outcome. To formulate nano-cutting fluids using GNPS and sesame seed oil as a base at various concentrations. To analyze the rheological properties of the formulated nano-cutting fluids and determine the optimal concentration. To perform a comparative study between pure minimum quantity lubrication, right? Understand the point, PMQL, right? And the graphene nano minimum quantity lubrication, GNMQL, technique in milling operations. To identify the optimal machining parameters for both PMQL and the GNMQL system. To devise and compare the ML predictive models for cutting temperature and surface roughness, evaluating their accuracy and performance in predicting machining outcomes. So what is the outcome of this machining process? Now you can see this is the proposed methodology, how this work was propagated, right? So I'm saying this particular area, experimentation result alone, we submitted a paper in a Q1 journal and it got published. So that is a important thing I want to say. I can share that paper. You can get more information, right, related to this work through that paper. Right after this presentation, I can share this paper to the organizers. Right. So here you can see the systematic study of this proposed methodology. So how we have to do the operations, right, to get a proper conclusion of this work. Now this is the experimental setup. Now you can see this is the experimental setup through which we get the results, right? This is about the LMW high-speed milling machine, right? And we have used the flare camera, and this MQL is the attachment, additional attachment that we did on our own, right? And it will pass the coolant to the cutting zone, and the thermocouple and flare camera both are used to measure the temperature sends to process during the machining. Now you can see this is about the workpiece and cutter type of material, how we are going to use this one, what are the major composition of the workpiece, and how this dimension of the end milling cutter and all right. Now this is the MQL equipment. The system features a 3-liter cooler. So only small portable one only we have developed. So 3-liter coolant reservoir along with an external jet spray nozzle. It is equipped with a filter regulator unit and an integrated pressure gauges. The equipment operates within the pressure range of 1.5 kg per centimeter square to 3 kg per centimeter square. It features an air pressure control knob for precise jet pressure adjustment and a 230 VAC solenoid valve that is used, right? So this is the our own design that we have did. This is the measurement of cutting temperature. So how to measure the temperature? It's a two type. One is the contact type, other one is the non-contact type. Both methods we have adapted. So a K-type thermocouple was used, right, to measure by means of contact type measurement. And non-contact type we have used the flare camera. The maximum recorded temperature values were chosen in the NIDAC system, and it is reported for the study. Next one is the surface roughness measurement. It is a Metatoya SJ401 surface roughness tester is employed to measure the surface roughness tester. We are reporting the arithmetic average, right, RA value that we have given, and the specification is reported here: 5 mm sample length and 0.0 mm cutoff length and all. And we did every machined surface, and the roughness value is reported. Now, dry milling experimental framework. The experimental framework is very, very important. So, researchers all of you are keep in mind because you are going to take some value, right, as input parameter. So, how do you choose this input parameter? There are different things. One is by means of previous literature, or otherwise the limitation of the machine, or the requirement of the applications where you want to go. So like this, and the other one is the specification given by the manufacturers. There are 4 different parameters associated with that. So you have to be careful while choosing the experimental what you call the experimental design, right? It is very important. So thorough literature is very important, and also what you call the yes.
കഴിഞ്ഞ പ്രാവശ്യം ഇതൊന്നും കഴിയാത്തതുകൊണ്ട് ഇത് മാത്രം ഇട്ടിട്ടാണ് കേരളത്തിൽ നടത്തിയത്. എന്നിട്ട് ടീമുണ്ട് ഈ കൈലപ്പിൽ മാത്രം നടത്തിയില്ല. Mr. Sibu Agustin? Sir, continue, sir. Please continue, sir.
Yeah. Actually, I think we can ignore their conversation. I think by mistake they are doing that. Yeah. Understand. Right. So the specification is very important. That you have to be very careful in selecting all these things. Another one is, so this is about the experimental number. So we have chosen, right? So different experimental accordingly we did this experimental design. Right. This is about the cutting speed, feed rate, right? these two are in our control, right? This is the input parameter. Where the cutting temperature and surface roughness, these two are the output responses, right? According to this, what you call experiment, we can get this cutting temperature is so much and surface roughness is so much. Okay, so these things we can take in account for this, right? Next one, this is another important thing. So the discussion or science behind the results. So that we have to do in a systematic way. Such evidence is very important. So how it should be? It should be XRA analysis. SRP confirms a graphene plane, right? Another one is from the SEM. So sheet-like structure with the fold, right? And a ring. So here that is witnessed through the metallurgical evidences. The metallurgical evidence is very important in giving the scientific report. Scientific report is very important accordingly, right? So what they are saying, right? The scientific report is very important. Then preparation and test of non-flame. Can you able to hear my voice?
ആ പ്രോഗ്രാംസ് എന്ന് പറയും ഇരിക്കാൻ പറ്റില്ല എനിക്ക് ക്ലാസ് ഉണ്ട് ബാബാ എന്ന് പറയുമ്പോൾ രാവിലെ ഇങ്ങനെ ലേറ്റ് ആയതാണ് കാര്യം ഇങ്ങനെ ഫസ്റ്റ് ലേറ്റ് ആയി പോയി ഇല്ലെങ്കിൽ നമുക്ക് രാവിലെ ഫസ്റ്റ് തന്നെ അപ്പൊ തീർന്നു പോയേനെ
Preparation and testing of non-flame. Someone can ask them to switch off their mic.
Yeah, now it is clear, sir. You can.
Yeah. It's actually, this is about the preparation and testing of non-flame. The cutting fluid are prepared in 3 different concentration of graphene nanoparticles such as 0.1, 0.5 and 0.8%. And this is the sequential steps associated in preparing that one, right? It may be by means of stirring, magnetic stirring, and we are getting the nanofluid, right? According to our requirement. This is about the comparative study of PMQL and GNMQL environment or framework that we have to. So this is the machining environmental PMQL and GNMQL. Cutting fluid seismic oil, graphene reinforced seismic oil. And cutting speed, it is 40, 50 and 60 meter per minute. Feed rate and depth of cut. Depth of cut throughout the process, it is constant, it's 1 mm. And the flow rate is given. And what about the jet pressure? These are all the input parameters that we can limit, right, or we can control on ourselves. Now, when you see the experimental results, this one, the last 2 columns, right? So the cutting temperature and surface roughness, these 2 are the visible response, output response, right, from this individual in experimental process, right? It may be the 80 number of experiments. You can see this is about the first 9 is PMQL environment. And the rest of the thing is GNMQL environment. And accordingly, the cutting speed and feed rate are given. So depth of cut I didn't mention because it is 1 mm throughout the process, right? So you can see the output of cutting temperature and surface roughness in micron. Then this is for the framework for statistical analysis. The experimental parameters were systematically arranged using Taguchi L36 orthogonal array. The optimization process was conducted using Taguchi signal-to-noise ratio methodology, employing Minitab 18 software. ANOVA was performed by evaluating the significance of factors influencing both cutting temperature and surface roughness. You can see this is about the machining environment, cutting fluid, cutting speed, feed rate, depth of cut, MQL flow rate, and jet pressure. Jet pressure we have varied 2 bar, 4 bar, and 6 bar. Feed rate also varied 0.01, 02, and 03. Cutting speed 40, 50, and 60 like that, right? So now you can see the corresponding results about the experimentation, right? Experimental design and corresponding responses for statistical analysis. This is very important for our analysis. Totally 36 experiments have been planned and we did accordingly, right? So these are the results for the total 36 experiments. Now, the data processing for ML models. So Python programming was used for feature engineering and the creation of ML models. The dataset dimensions are checked, revealing 36 rows and 6 columns. So someone asked about the L36, L27. It depends on the factor of safety. So it was verified that were no null values and in the data set. A histogram was used to assess the distribution of numerical variables, and box plots were employed to identify outliers. The relationship between variables were analyzed using correlation heat map. The Gaussian data arguments technique was employed to mitigate overfitting caused by the limited data sets. The data set was divided into X for explanatory variables and Y for the response variables, cutting temperature and surface roughness, right? The standard scalar technique was applied to ensure all the features contributed equally to the learning process and to improve model performance. This is the methodological approach for ML model. So here you can see the multiple linear regression, MLM. MLM method used to predict the value of one variable based on two or more other variables. It fits a straight line that best describes the relationship between the input and the output. Then k nearest neighbors, KNN, predict a value by finding the k nearest neighbors to the data point. It looks at the values of those neighbors and chooses the most common one. The predicted value is then based on its majority or average. Random forest regression, RFR, is a machine learning algorithm that builds multiple decision trees to make predictions. Each tree makes its prediction, and the final results is the average of all the trees' predictions. This helps improve accuracy and reducing overfitting. Grid search cross validation. It is a method used to find the best model parameter by testing multiple combinations of hyperparameters. It evaluates each combination using cross validation to improve model accuracy and avoid overfitting. Data augmentation. So this data augmentation enhances limited data sets by generating synthetic data. Gaussian data augmentation achieves this by adding the Gaussian noise, improved model generation and performance. So this is about the methodological approach for ML models, RFR working principle. Random forest regression is an ensemble machine learning algorithm that uses a collection of decision trees to make predictions. It combines the predictions from multiple trees to improve accuracy and reduce overfitting. These advantages of this model, random forest regressor provides high prediction accuracy by aggregating the outputs of multiple decision trees, reducing overfitting. It effectively models complex and non-linear relationship between input features and the target variables. The model is robust to outlier and noise, as averaging across trees, minimizing the impact of anomalies. It handles both numerical and category data without requiring extensive pre-processing. Random forest can estimate features importance, which helps in understanding the influence of each input variables. It performs well even when some data is missing, offering resilience in real-world scenarios. The model scales efficiently with large data set allows for parallel computation, making it suitable for high performance applications. This KNN model, where K nearest neighbor is simple to understand and easy to implement, requiring no assumption about the underlying data distribution. It is a non-parametric model, which makes it suitable for both linear and non-linear data patterns. KNN can be used for both the classification and regression tasks, offering versatility across problem types. The model adapts naturally to changes in the training data sets as it stores the entire data set and makes decision based on proximity. It performs well with the small data sets and when the decision boundary is irregular or complex. KNN does not involve a training phase, which reduces computational time during model building. The method provides high interpretability as predictions are based on similarity to nearby data points. This is about the KNN working principle. It's a supervised learning algorithm used for classification and regression problem. It works based on idea of similarity. The outcome for the new data point is predicted based on the outcomes of its nearest neighbor in the training data. This is about the multiple linear regression model. It's a statistical technique used to model that linear relationship between one dependent variables and two or more independent variables. You can see the MLR, multiple linear regression working examples here, and so on. Then evaluation metrics for ML models. Machine learning model evaluation metrics quantify how well a model performs. That is the underlying point. So providing insight into its accuracy, efficiency, and suitability for the task at hand. These metrics help compare different models and algorithms, ensuring that the chosen model is accurate, dependable, and appropriate for the specific problem. This is the evaluation matrix for ML models. It's a mean absolute error. So it measures the average absolute difference between predicted and actual value. Lower MAE means better accuracy. Mean squared error, it calculates the average of squared differences between predicted and actual values. Root mean squared error, so it measures the average size of prediction errors. The lower RMSE, the closer the model predictions are to the real values. Mean absolute percentage error, it expresses prediction error as a percentage of actual value. Coefficient of determination, it shows how well the model explains the variability of the actual data. And accuracy, it means the proportion of correct prediction out of the total prediction made. You can see the appropriate equations for the models and all. Now I come to the conclusion. So what are the, now you can recall the objective, what I proposed during my work, and now it is reflected in the conclusion and how, what I have got that that I can do in a detailed way. Influence of machining conditions on cutting temperature and surface roughness in dry machining. That was the first case without any lubricant. You can see the supporting graphs, right? The experiment yielded a peak temperature of 297 degrees centigrade under dry machining conditions because there is no coolant used, where the cutting speed was 60 meter per minute and the feed rate was 0.02 mm per revolution. This notable increase in temperature during dry machining can be attributed to the elevated frictional forces within the cutting zone, a result of absence of coolant. Yes, that is important. The minimum cutting temperature, 118 degrees centigrade, occurred at 40 meter per minute and 0.01 mm per revolution due to reduced friction and heat generation from the low cutting speed and feed rate. The highest surface roughness value of 1.226 microns, you can see in the second graph, was observed at the cutting speed of 50 meter per minute and a feed rate of 0.01 mm per revolution. Low feed rate limits chip thickness with a moderate cutting speed, promotes built-up edge formation on the tool, resulting in surface irregularity. Yes, so the dimension of the tool nomenclature will be changed, which will lead for more surface irregularities on the new machined surface. A minimum surface roughness of 0.703 micron was achieved by 50 meter per minute cutting speed and 0.03 mm per revolution feed rate, etc. And it goes. Now you can see about the chip morphology in dry machining process and each condition. So it is very important, metallurgical evidences for the chip morphology at each machining conditions. According to the examination of chip, there are scratches on the face. The cohesive force aimed to ASAH11 and the tool produces the scratches. While chip flow workpiece got scrapped due to the extensive hard particles on the tool interior. High cutting speed and increased feed rate, fragmented chips are more likely to form due to excessive strain and localized heating. There is no chance for continuous chip. It is not ductile material. The hairy layer of chip on dry machining condition is evident of more ductile structure. Then you can see at the high temperature feed rate, the chip appeared curved due to increased heat, lack of lubricant, and heat transfer at the tool-chip interface. At low cutting speed and low feed rate, continuous chips are formed due to smooth and stable sharing of material. Right? You can see the first one, that is a serrated one. The purple colored chips were observed at high cutting speed and feed conditions. Now it is about the nanofluid preparation, testing and a comparative study of PMQL and GNMQL. This is the first case study is over. This is the next one. Now analysis of thermophysical properties of the cutting fluid. The thermal conductivity increased with a higher GNPS concentration due to the superior thermal properties of the GNPS compared to vegetable oil. The thermal conductivity value of nanofluid at 0.8% concentration is the maximum. The surface tension value influenced by GNPS concentration and it decreased with increased value. Then owing the attraction between the higher intermolecular energy of nanofluid of surface tension, the value decreased within the concentration. The penetratability of nanofluid is enhanced due to the less surface tension value and which leads effective way of lubrication in the cutting zone. The density increased with the GNPS concentration measured and so on so, and the highest viscosity value is 86.12. The thermophysical property analysis revealed that GNPS with the 0.8% weight exhibited potential results among all. Right, so that is the conclusion we made by using this study. Then influence of machining conditions on cutting temperature in PMQL and GNMQL environment. Now understand the concept. Now we are introducing the coolant. Those previous case there was no coolant. Now you can see the cutting temperature is lowered by 55%. 297 to 142. In this case it is 142. Earlier case it was 297. So approximately 55% of temperature is decreased through enhanced lubrication. While GMQL is nanoparticles further cooled to 90 degrees centigrade, totaling 54.3 drop from the dry machining when compared with the dry machining process. This notable reduction can be attributed to the lubrication effect, which facilitates convective heat transfer with minimal but effective lubrication supplied in PMQL system. The introduction of nanoparticles augmenting the lubrication and the thermal properties of the cutting fluid in GNMQL environment. The lowest temperature recorded in the GNMQL conditions was 59 degrees centigrade at a cutting speed of 40 meter per minute and the feed rate of 0.01 mm per revolution. The cutting temperature rise is attributed to increased spindle speed and so on. The cutting higher temperature is noted at 0.02 mm per revolution feed rate compared to 0.03 mm per revolution. This is due to increased contact time between tool and workpiece. So here you can see the surface roughness. Another parameter is surface roughness. Earlier it was the cutting temperature, now surface roughness on the same environment, right? So under PMQL, surface roughness reduced significantly 0.3597 microns from 1.227 microns in dry milling. Right, 70% decreased. So smooth surface we have attained by using this one. This improvement is due to effective lubricant film in the cutting zone. It helped to reduce the tool wear and build up its formation, enhancing the surface quality. The lowest surface roughness value of 0.258 micron was attained by cutting speed of 40 meter per minute and feed rate 0.01, right? This represents 9.8 enhancement in surface quality relative to PMQL. See, so our core job is the real-time experimentation. Modeling is the portion of your thesis, right? In my point of view, it may be 80-20 or 90-10, right? So, but the prediction is very important. So that is the very approachable, right? By using the n number of data. Right. The improvement is linked to the enrichment of the lubricating fluid with the spherical shape GNPS which provide a rolling action between the cutter and workpiece. GNMQL system enhances surface quality at low speed and feed by allowing nanoparticles to penetrate tool workpiece interface. And in that way, we claim that the superior surface finish is visualized or realized by adding this environment, GNMQL environment. This is the chip morphology of PMQL and GNMQL environment. So it compares to dry cutting environment. PMQL and GNMQL environment produces only few narrow scraps in the chip surface. Reduction of scratches on chips will impact the better surface finish and improve tool life. Owing to addition of GNPS, the GNMQL creates less fibrous structured chips and ensure the development of brittle chip structure compared to others. Then the GNMQL shows what do you call? They're calling for some other meeting. Okay. Yeah, so less serrated chips formation than PMQL due to better heat dissipation and lower temperature by GNPS. Now the statistical analysis and the comparative study of ML model, which we are going to discuss now. Here you can see this is the influence of cutting speed, feed rate, and MQL jet pressure on cutting temperature in the PMQL environment. You can see the supporting graph, which will give a detailed information about the appropriate experimentation results. An effective decrease in cutting temperature is achieved with an elevation in jet pressure, reaching optimal efficiency at 4 bar pressure. Another one is, when you see here, the optimum pressure ensures finer oil mist droplets, improving lubrication and reducing friction in the cutting zone. The reduction in temperature remains effective until 6 bar pressure threshold, beyond which a temperature increase is observed. This temperature surge is attributed to excessively high air pressure inducing in spring-back effect of droplets from the cutting surface, resulting in ineffective lubrication process. The highest cutting temperature is observed is the highest feed rate combined with lower MQL system, whereas the lower cutting temperature occurs at lowest feed rate with the minimum MQL pressure and so on. Here this indicates that lower feed rate, a moderate MQL pressure provides optimally reducing friction and heat generation. Lower cutting speeds and feed rate reduces cutting temperature, while higher value increases them as slower movement allows better cooling across the cutting zone. Here you can see influence of cutting speed here on the feed rate and the MQL jet pressure on cutting temperature in GNMQL environment. So cutting temperature is significantly lower across all cutting conditions. Down when you compare, down generically PMQL due to the superior thermal diffusivity of GNPS. That is the important point here, enabling rapid heat dissipation. So heat dissipation is more when compared to the other mechanism. This reduction is attributed to the rapid heat propagation facilitated by the exceptional thermal diffusivity property of GNPS in the GNMQL environment. So this is the Brownian motion of GNPS enhances coolant dispersion, overcoming the inadequate cooling seen in PMQL at high speed. So PMQL at high cutting speed and feed rates, it is inadequate. That is the inference we are going to submit after this experimentation. The lowest cutting temperature of 55 degrees centigrade was achieved under optimal machining conditions, GMQL environment, cutting speed 40 and feed rate 0.03 and MQL jet pressure 4 bar. This is about the same for the surface roughness in the PMQL environment. So understand the concept. So two different parameters we have taken for the output response. So one is the cutting temperature, another is the surface roughness. Each one is described in a systematic way. Right? So surface quality improves with the improving cutting speed up to 4 bar pressure due to better chip evacuation and efficient heat dissipation, preventing thermal damage. In the 6 bar pressure region, surface roughness slightly increased compared to 4 bar region due to ineffective automation, leading to poor lubrication, high friction, and elevated temperatures. Excessive pressure, on the other hand, may wash away the lubricant from the milling zone, increasing resistance and temperature and negatively impacting the surface finish. Optimal surface quantity or quality is achieved at reduced feed rates and cutting speed, minimizing the generation of built-up edge on the cutter. The higher cutting speeds and feed rates result elevated surface roughness due to inconsistent cutting forces caused by tool deflection. Actually, cutting force also we can take, but we didn't take this one. That by means of instrument cutting force dynamometer we can use. That we can take. So this is about the surface roughness in GNMQL environment. The introduction of spherical shaped nanoparticles between the milling cutter and workpiece facilitated a rolling action, substantially reducing resistance, wear, and heat generation during cutting operations. Consequently, this resulted in lower cutting surface roughness value across all speed conditions compared to the traditional PMQL conditions. A higher surface roughness was recorded in 2 bar pressure region. So everyone is reported here, right? Indicating insufficient flow and dispersion of the nanofluid due to agglomeration. This phenomena adversely affected the surface quality. Minimum surface roughness occurred at 0.01 mm per minute, feed rate at high pressure, likely due to better penetration of lubricant and nanoparticles into the cutting zone. Lower cutting surface finish was observed at lower machining parameter conditions and vice versa. The enhancement in surface quality is due to polishing and surface repairing effect enabled by the nanoparticles. The lowest surface roughness of 0.0172 micron was achieved with optimal machining conditions, which included a GNMQL environment, a cutting speed parameters, that is, the input parameters are 60 meter per minute and feed rate 0.01, and so on. This is about the Taguchi-based analysis of optimum parameters for cutting temperature and surface roughness. The optimal end milling process parameter for achieving improved cutting temperature are identified by the GNMQL cooling environment at a speed of 40 meter per minute, feed rate 0.01 mm per revolution, and 4 bar MQL jet pressure. The cutting speed exerts the predominant influence on cutting temperature, followed by MQL jet pressure, with the cooling conditions exhibiting a comparatively lower impact. The hierarchical order of influence of milling factors in the cutting temperature, you can see that Pareto chart when you go for this Pareto chart, which is the most influencing factor and least influencing factor, right? So that is in that way. It is the cutting speed, jet pressure, cooling conditions, and feed rate. That is the least significant factor is feed rate. The optimum parameter for enhancing surface quality are identified with the GNMQL cooling environment at a cutting speed 40 meter per minute and feed rate 0.01 mm per revolution and 4 bar MQL jet pressure. The least impactful factors for surface smoothness are cooling conditions and feed rate. The order of influence for each parameter is determined in the cooling conditions A, MQL jet pressure D, and cutting speed B, then feed rate C. So this is about the mean value, and you can see for the surface roughness, earlier it was temperature, this is surface roughness, and now for cutting temperature and surface roughness, this is the feature engineering insights for cutting temperature data. Analysis of distribution plot reveals the speed, feed, and MQL pressure exhibit uniform distribution. A positive skewness is evident in the frequency distribution of cutting temperature. The skewness is attributed to the prevalent occurrence of temperatures within 100 degrees centigrade to 130 degrees centigrade range, attributed to the utilization of PMQL and GNMQL technique. In the box plots, no outliers were detected in the speed, feed, and MQL pressure data. The outliers are observed in the cutting temperature box plot, particularly in instances of PMQL machining conditions. Right. In the heat map, the Pearson correlation coefficient of 0.7 indicates a strong positive correlation between speed rate and cutting speed. A weak negative correlation of minus 0.033 is identified between feed rate and cutting temperature. A negative correlation of 0.17 is noted between MQL pressure and cutting temperature. Now you can see the feature engineering insights for cutting temperature data and heat distribution. Right, box plot is witnessing. This is what reported there, right? This is about the surface reference data. The distribution plot shows that cutting temperature, cutting speed, 40, 50, and 60, feet at 0.01, right, 0.2, 0.03, and MQL jet pressure 246 bar are uniformly distributed. The surface reference distribution shows positive skewness with the most values between 0.25 to 0.38 microns due to PMQL and GNMQL use. Higher values 0.43 to 0.53 are linked to ineffective jet pressure. It is the inference from our study. The analysis of box plot reveals that no outliers are found in the speed, feed, and MQL jet pressure. On the other hand, outliers are evident in the surface roughness box plot, especially under PMQL machining conditions. Heat map indicates a strong positive correlation 0.31 between surface roughness and cutting speed. A weak negative correlation of minus 0.041 is observed between surface roughness and MQL jet pressure. An extremely weak negative correlation of 0.000 is extremely weak negative is observed between surface roughness and the rate and appropriate evidences which we have want to show by using this distribution plot and box plot is presented here. So this was reported there. Then development on the comparison of ML models for cutting temperature. During the development of the ML models, 80% of the data was utilized for training and the remaining 20% was retained for testing. The initial ML model was constructed by utilizing MLR model, so the appropriate equations are presented in the earlier. Right, you can utilize the ML model regression equation is T is equal to so and so, right? So that we have arrived, right? We have used the Python programming and we got the results. In the RFR model, hyperparameter toning yielded the following optimal values: a maximum depth of 20 and a minimum of 1 sample per leaf. 5 samples required to split a node and 200 estimators. This model KNN model was performed by evaluating different values of K along with the two distance matrix, erudition and Manhattan, and two weighing schemes, uniform and distance based. The optimal configuration was achieved with the 5 neighbors and so on, and the result is reported here. So development and comparison of ML model for cutting temperature, you can see MAE, RMSE. The R4 model delivers impressive results, achieving a MAE of 3.7, MSE of 338. So and so on. You can see this is the values, abbreviated values are given, R square value of 0.88 like that. This performance is due to the ensemble method, which combine multiple decision trees to enhance prediction accuracies. MLR model recorded the lowest metric scores with the MAE at 7.5, MSE at 94, RMSE at 9.7, and so on. This poor performance due to the linear assumption, which limits its ability to capture complex or nonlinear relationships. KNN model attains the highest metric scores, right? And this value is reported with an accuracy of 97.4. So here you can see RFR it is 95.3 and MLR it is 90.15 and KNN it is 97.4. KNN performed well due to its ability to capture local patterns using proximity-based classifications, enabling accurate responses to suitable data variations. So this is about the models and its comparison. That's it. I will share the paper. When you go through the paper, you can get a lot of information related to that one. All the things what I have presented, that is available in the paper, right? So this is about the development and comparison of model for cutting temperature. What is the actual and predicted, and it is presented here, right? How it should be according to the sample number and cutting temperature. It is there. So this is about the ML model for surface roughness. MLR model established a predictive equation for surface roughness. The REA value is listed here. The optimal 4 samples per leaf. A minimum of 10 samples are kept to split an internal hole and a total of 50 estimated. The KNN model number of neighbors was set to 5, uniform weights were applied, and the p-value was set to ensure optimal performance. This RFR model demonstrated, and it is presented here. This performance is mainly due to the ensembling approach, so which reduces variance by combining multiple decision trees for more stable and accurate prediction. You can see this one MLR 9%. The lower percent between variables unless explicitly defined, leading to oversimplified results. KNN model outperformed to others, achieving the highest performance with the other values ME, MSE, and R, and reported that the accuracy is 92.9%. It is superior. Results stem from its non-parametric nature, which enables it to effectively capture non-linear relationships without imposing strict assumptions on the data distribution. This is the comparison of this one, and this is about the sample mala, RFR, and KNN. So you can able to understand how it should be compared at the end. So the potential applicability that should be witnessed by how much accuracy is projected by the real-time application, right? By and compared with the real-time application. This is about the confirmation experimentation. So this confirmation test compared with the KNN predicted value. This may be the output response to cutting temperature and surface roughness. A1, B2, C2, D1, it is payments of the Taguchi design. Then predicted value KNN model 58, experimental value 56, difference is 2, and the surface roughness is like that. And the corresponding some images of the machined surface according to this condition. This one we took it from the PhD deck, right? So scratch model, how it is there, and smooth surface, how it exposed, right? So those things are done. Now coming to the conclusions, when you see, so a peak temperature of 297 degrees centigrade was observed under dry machining at 60 meter per minute. And 0.02 mm per revolution. The absence of, in that case, there is no absence of lubrication, right? So the minimum, I just want to summarize quickly because just so you should know what is what, how you have to proceed a research, right? That is very important. The minimum cutting temperature 118 was recorded at 40 meter per minute and 0.01 mm per revolution. A higher surface roughness 1.21 micron was observed at 50 meter per minute, 1.01 mm per revolution. The minimum surface roughness was 0.703 micron was recorded at 50 meter per minute and 0.03 mm per revolution. Continuous chips are produced under low cutting speed and feed rate, right, as the material undergoes steady and uniform shearing during the machining process. So purple colored chips appeared at high cutting speed and feed due to intense heat generation. That's what there is a science behind that one. We can say this is the continuous chip, this is the continuous chip. Why? What went wrong, or why it occurred? What is the reason for that? That we have to discuss in detail. So finding of nanofluid preparation, testing and a comparative study of PMQL and GNMQL environment. So the thermophysical property analysis revealed that GNPS was 0.8%. Among 3, 0.8 exhibits potential results. PMQL lowered with the cutting temperature of 27.9, enhancing lubrication and cooling. GNMQL further reduced it to 90 degrees centigrade. Under GNMQL, the lowest temperature, you can see this is 59 degrees centigrade, was recorded at 40 meter per minute and 0.01 mm per revolution. PMQL reduces surface roughness also 70.7% decrease compared to higher values. And in the dry milling, due to improved lubrication that minimized built-up edge formation and tool wear. GNMQL achieved the lower surface roughness of 0.258 microns at 40 meter per minute, and 0.01 mm per revolution, improving by 9.8% PMQL due to JNPS, enhancing lubrication, heat dissipation, and wear resistance. PMQL and JNMQL environment due to improved cooling and minimized notch formation. This GNMQL environment generated fewer serrated chips than PMQL, owing to nanoparticles rolling action and the formation of protective tribofilm on the tool chip interface. This is about the cutting temperature decrease of both PMQL and JNMQL as jet pressure increased. The 4-bar yielding best results than other things. Minimum surface roughness of 0.172 micron was obtained under optimal conditions using GNMQL setup with a cutting speed of 60 meter per minute, feed at 0.01 mm per revolution, and so on. It goes. Based on Taguchi-SN ratio, GNMQL environment achieved optimal results for both cutting temperature and surface quality at 40 meter per minute. It is the finding. ANOVA results for cutting temperature show that cutting speed is dominant factor responsible for 70.779 variation while MQL jet pressure. The KNN model, yes, the KNN model delivers the best results for predicting cutting temperature with all these things, and is 97.4% accuracy in case of cutting temperature. And again, improved most effective surface reference prediction also in both cases, right? So, and it exhibits 92.9% of accuracy. Its edge lies in handling nonlinear pattern without assuming a specific data distributions. So, before wind up the session, I would like to show the paper. This is about the data pre-processing. Maybe I can share it to Ramohan. Maybe you can collect these details. And the paper also, this one is the paper. This paper, if you see, you can get all information what I presented here, that you can understand in detail the machine learning prediction of surface roughness and sustainability of information from this paper. This is published in Smart Materials in Manufacturing, which is a Q1 journal. And I will also pass this one to the organizers, right? So you can all get all this information through this paper, right? So this I would like to thank the organizers for giving me the opportunity. Thank you very much.
Thank you very much, Professor. So now let's start with let's start questionnaire section. So dear participants, so do you have any questions, clarification or doubt? Just
Yes, sir.
ask to Professor Uday Kumar. Meanwhile, sir, Professor, there is a question in the chat
Yes,
box.
sir. Yes.
Yes, sir.
Okay.
Shall I read it, sir?
I'm seeing a nice presentation. Thank you. So some questions, L36, L27, these are all based on the factor of safety of the parameters which we have used, right? And so I don't have the exclusive presentation for the random forest prediction. I don't have, because it is a combined one what I presented, that only I have. Yeah, it is. We can apply ML model for L16 orthogonal array also. There is no thermal conductivity in different concentrated thermal conductivity we can do by what you call experimentation. We can able to do in case of a different concentrated fluid according to the requirement. So this is what I say. This we have prepared on our own GNMQL environment, that we have prepared everything, and we did the experiment at what you call LMW machine, high speed machine. But since it is a conventional machine only, but the concept is we have used the cutting in a different manner, and also workpiece material is a hard material. This environment is new, right? That we have used as an attachment in the particular machine. So no machine is with the same fuel supply as such. Okay, sir.
Yes. So dear partners, do you have any questions? Oh, shall we conclude, sir? Yeah. So thank you very much, Professor, for the highly
Yes, sir.
informative, insightful session. Your valuable presentation on machine learning prediction for surface toughness in sustainable machining has certainly provided new perspective for all the participants. So with this, thank you very much, Professor, for accepting our invitation and giving wonderful information to all the participants.
Yeah, I want to say, if you want to go for this model and all, you should have a thorough experimentation to get the real-time experimental results. That is my request to all the researchers. So once you get a number of data, you can go for any kind of model that will give a reliable output or reliable things for the reliable, that will give the reliable predictions in future.
Yes, sir. Absolutely, sir. Whatever you said, that is true. So, with this, we come to the end of the day two, session 2 of the FDP. So, we look forward to the active participation of all the attendees in the upcoming sessions. Thank you all for joining us. Thank you very much,
Thank you, sir.
Professor, and
Thank
all.
you, sir. Thanks a lot. Thanks a lot.
Thank you very much, Professor.
Yeah. Thank you.
Dear participants,